Today's modern interactive multimedia experiences, applications and services rely on low levels of latency to deliver immersive real-time experiences to end users. One of the challenges that we face in modern networks, and particularly in mobile networks, is how can we ensure that this delay critical traffic is handled accordingly? And how can we ensure that the user's experience is not degraded by congestion issues within the network? And this is where L4S comes in. L4S is low latency, low loss, scalable throughput. And it's a mechanism within networks that allows for delay critical traffic to be prioritized, but also congestion in the network to be managed in a dynamic and scalable way. Now, when it comes to some of the key use cases that we're likely to see that will utilize L4S, if we focus firstly on these kind of multimedia experiences that I mentioned earlier. So for things such as high quality immersive video calling, this may not simply be static video calls between two people. This also includes conferencing scenarios and perhaps even holographic telepresence in future. We've also got cloud gaming that of course relies on low levels of latency to deliver low lag gaming to end users. So with cloud gaming services, the user is being streamed a video stream and the processing is being handled on a remote server. So the faster the connectivity, the less input lag is seen and the better the quality of the end user experience. And then finally, we've got the type of immersive experiences that we see with augmented reality, extended reality, and also virtual reality. Now, these experiences are particularly delay critical. Any input delay to a VR headset, for example, can potentially induce motion sickness in users, but ultimately will degrade their experience. So each of these use cases relies on their traffic being able to get through the network in an efficient and a delay responsive way. So if packets associated with these applications and services are stalled within the network, then we start to lose that real-time element that makes them so immersive. So we're starting to see L4S deployed as a solution to support the needs of delay critical applications. And it's not just immersive multimedia applications. We may also see this in other delay critical and low latency scenarios. L4S aims to address some of the key drawbacks of more traditional congestion control algorithms that simply were not designed to meet the needs of modern real-time delay critical applications. L4S itself consists of three key components. We've got low latency. So with L4S, we are able to prioritize delay critical data packets with minimal delay to ensure that we can deliver real-time communication that is required by some of the key multimedia applications that we discussed earlier. L4S is also able to reduce loss within the network. So rather than traditional methods that rely on packet loss to signal the presence of congestion within the network, L4S aims to manage this in a more efficient way. And it does this by eliminating bottlenecks and keeping queuing times low for L4S critical traffic. And then finally, we have scalable throughput. So with L4S, we can optimize the amount of available bandwidth and we can ensure that all packets are treated fairly. So it's important to note that L4S doesn't just prioritize delay critical traffic. It needs to strike a balance between delay critical L4S traffic, but also classic traffic within the network. So the key thing here is that we strike a balance between delay critical traffic, but also classic traffic, which may have some time frame requirements, but is less delay critical than what we see in the L4S traffic flow. One of the key drawbacks of traditional congestion control algorithms is that they are something of a blunt instrument when it comes to managing congestion. So as queues build within buffers in the network, we wait until packets are starting to be dropped. In other words, these buffers and these queues are actually full. So packets are not being transmitted within a given time frame and thus are being dropped. The problem with this is it's something of a blunt instrument. When packets are dropped, we signal to the sender that they need to cut their congestion window, so the amount of packets that they have in flight at a given time, by half. So effectively, they reduce their sending rate by 50%, which in some instances may be too drastic a reduction. And the problem there is the sender will then build up the sending rate quite slowly, which can lead to underutilization of available bandwidth. So really, L4S solves the problem of balancing the needs of different applications in a fair way and ensuring that delay critical traffic has special treatment effectively to ensure that where possible, this traffic is prioritized over other classic traffic. Now, the mechanisms that underpin L4S, well, there are two. We've got explicit congestion notification and we have dual queue coupled active queue management. Now, neither of these things are L4S specific and neither are specific to mobile networks. So these are concepts that exist in networking and they are being used to underpin the approach that we refer to as L4S, but really is a combination of different factors. So with explicit congestion notification, we are able to effectively mark packets as being L4S traffic using explicit congestion notification. So a sender will mark a packet as ECT, ECN capable traffic, and this means that we know that this packet needs to be associated with an L4S flow within the network. Now, we also have the ability to mark packets within the network as CE or congestion experienced. And this is what is used to signal congestion. So rather than relying on packet loss when queues and buffers get full, we actually take a much more proactive approach and we try and stop these buffers from becoming too full. So effectively, and we'll get into more detail later on, we signal to the sender that there is congestion in the network and the sender is able to make small adjustments to their sending rate. So in the example of potentially video streaming, what will happen is the sender may adjust, so this could be the application server for a video streaming service, will potentially adjust its bit rate to reduce the amount of data or the amount of packets in flight. And then once congestion is reduced, we can then increase that sending rate. The key thing here is that we don't overload queues within the network because this will lead to standing queues and the issue of buffer bloat. So explicit congestion allows for the marking of packets to say that there is congestion in the network, and this happens much earlier than what we would see if we used packet loss as an indicator for congestion. And the second component, dual queue coupled active queue management. This really is about how we treat L4S traffic versus classic traffic. And we need to uphold principles of fairness within the network. So it isn't a case of we hold all traffic back and allow delay critical applications to really use up all of the available transmission link. No, we use intelligent queuing to manage the traffic. So this notion of dual queue is we have L4S traffic and we have classic, i.e. non-L4S or non-delay critical traffic. And we use an algorithm to ensure that the traffic is treated fairly and that an even balance or an equal balance of packets is allowed through from both the L4S queue and the classic queue. So both of these two technologies in combination really are the key underpinning technologies behind L4S. Now, before we delve any deeper into L4S, it's worthwhile to explore some key concepts when it comes to measuring delay within networks. So we'll start off with latency and round trip time. So latency is the amount of time it takes for a packet to travel from a source to destination, or a sender and receiver. And we measure round trip time as the time it takes to send the packet, but also to receive a response. So in this scenario, we send out a request and we at some stage receive a response from the destination. So this may be communication between a mobile device and an application server, for example. And this data may need to travel through the mobile network and ultimately out to perhaps an application server on the internet, for example. So there are different factors that will influence the amount of delay that we experience. So in this scenario, if we were to measure both request and response time, so the outbound leg, if we've got 800 milliseconds of latency, and with the inbound we've got 900 milliseconds. So the total latency in this scenario is the sum of the outbound latency and the inbound latency. So in this case, our total latency, or sometimes referred to as round trip time, is 1700 milliseconds or 1.7 seconds. Now, this may be acceptable for the application that's being used in this example, or there may be delay critical applications where this is simply too high a level of latency. Now, there are several factors that do influence latency. So we've got propagation delay. So this is the time it takes for the signal to travel across a particular medium. So even across high-speed fibre optic links, this will be influenced. There are transmission losses and transmission delays based on the distance that the data needs to cover. So with propagation delay, this could refer to fibre, it could be a copper cable, or of course with mobile networks, it could be an air interface. Next, we've got transmission and processing delays. So this is the time spent encoding, routing, switching packets on the network, because of course the data isn't travelling in a straight line with no obstacles in its path. And particularly on the internet, we're likely to see lots of different hops and lots of different points at which data is being switched. And of course, we have encoding and decoding to consider, which will contribute to the overall latency. And then finally, we have queuing delay. So this is the time that packets spend waiting in buffers, for example, or queues when the network is congested. So this is the problem that L4S really aims to solve. And the thing with propagation delay and transmission and processing delay is we don't really have a great deal of control over that. But what we may be able to control is this third element, this queuing delay. So I've mentioned already this concept of buffer bloat, where packets start to build up in buffers on routers and delay critical traffic can get stuck behind. And of course, this can have quite a significant negative impact on the end user's experience. So it's a little bit like if you're stood in line at a supermarket and everybody in front of you has got trolleys full of shopping and you have this urgent product that you need to buy. Maybe it's some medication or something like that you absolutely need to buy. It's essential that you get it bought quickly. But you're stuck in the queue behind lots of people who aren't particularly in a rush and have got lots of shopping that needs to be processed. So that's kind of an illustrative example of the issue of buffer bloat, where delay critical packets kind of just stuck behind traffic that isn't particularly delay critical, but did get there first. And we'll explore this concept in more detail later on. So this is where we're really going to focus our efforts in terms of driving down latency, is on this queuing delay, since the first two are kind of set. There's always going to be some overheads when it comes to the transmission of data based on either the transmission medium or the processing that needs to take place along the way. Now, the next concept that we'll consider is jitter. Now, even in situations where latency is fairly low, the amount of jitter can have a negative influence on the delivery of delay critical packets. So what do we actually mean by jitter? If we consider a scenario where there is no jitter at all, what we would see is packets are sent at uniform time intervals. And this is great for real-time communication, since the data is arriving in a predictable way. There is fairly short delay, presumably in this example, and packets are arriving in an orderly fashion, and kind of in this illustrative example, they're kind of evenly spaced. Now, when we experience jitter in the network, what that actually means is that we see a variation in the delay of received packets. And this can be particularly problematic in real-time scenarios. So on a voice call, for example, if packets aren't being delivered on time, or if there is a long delay time while we wait for a packet to be delivered, then clearly this is going to have a negative impact on the quality of a call and may even lead to the call being dropped. Now, there are ways that we can mitigate the effects of jitter, so jitter buffers, for example, but we're still quite limited in terms of what we can do if the jitter rate is particularly high. Now, we also need to consider packet loss itself. So in packet loss, what we see here is we've got our packets of data in flight between the sender and receiver, or the source and destination. And with packet loss, we may see packets that don't make it for whatever reason. So this may be down to things such as congestion in the network, or packets not being delivered within a particular time frame, for example. And again, this is problematic in a real-time scenario, because unlike non-delay critical situations, so downloading emails or downloading a file over the internet where the packet can simply be requested again, in a real-time scenario, really once that packet has been dropped, it's dropped. And again, there are mechanisms that we have in place within mobile networks that can reduce the impact of packet loss. But in the same way as we had with Jitter, this is going to potentially have an impact on the quality of a call or an experience within a cloud gaming service or a virtual reality service, for example. So with real-time communication, we are less tolerant of packet loss because we don't really have the time to ask for the packet to be sent again. And there are a number of situations and a number of causes of packet loss. So I've mentioned already congestion, but we also see things like hardware issues along the way, potentially. We see poor signal quality, which may, of course, be an issue within mobile networks and within Wi-Fi networks. It could be down to malicious attacks, such as denial of service attacks. It could even be down to software bugs as well. But really the number one cause of packet loss is congestion. And again, L4S attempts to address this within networks. Congestion control mechanisms in networks seek to regulate data transmission and ensure that bandwidth is being used efficiently. Now, we've mentioned already that one of the problems that L4S solves is the problem of queuing packets within buffers and also how we can deal with congestion in the most efficient way. Now, if we consider traditional or more classic congestion control mechanisms that we see, so things such as TCP Reno, for example, the way that they work in a general sense is that they rely on packet loss to signal congestion. So in the case of TCP Reno, for example, when the sender sees 3 acknowledgements that it receives back from the receiver's end, it understands that packet loss is taking place in the network and it will adjust its sending rate. And we'll talk in more detail about the extent to which it does that, but also why it's a problem in modern networks. So the sender sends out packets, the receiver will provide an acknowledgement that says, this is the last packet that I've received, I'm expecting the next packet. And if the sender sees 3 of those in a row, it understands that this isn't just a case of packets being received out of order. It understands that packet loss has occurred. It will automatically retransmit the missing packet, and it will then seek to reduce its sending rate or its congestion window. So if we compare the two mechanisms then, so L4S fundamentally relies on a congestion control mechanism called TCP Prague, and this is an evolution of the earlier Reno standard that was used for congestion control. And it's worth mentioning that there are several different ways of managing congestion within a network and several variations that are used by TCP, Transmission Control Protocol. Okay, so comparing classic congestion control to the mechanisms used in L4S then. So we can see the congestion signal, as I've mentioned already, it's based on packet loss. Within L4S, and we'll explore this in more detail, this relies on explicit congestion notification. And without going into the specifics now, ultimately this means that the transmission can be regulated in a much more efficient way. So rather than waiting for packet loss to occur, by which point it may be too late to really control the congestion, we take these frequent ECN marks to signal that, hey, congestion is building in the network. So we haven't hit the limit, buffers are not full, queues are not spilling out of buffers. We're actually saying, okay, we're getting a little bit congested. Maybe you could just dial the sending rate back a little bit. So it's a much more graceful way of handling congestion in the network. Now, in terms of the response that we see when we encounter congestion, so with classic congestion control, it's a very reactive approach. So it's very much trying to close the gate after the horse has bolted. And in other words, we're taking action, but perhaps a little bit later than would have been optimal. Now, as I mentioned already, L4S is very, very proactive. So it will signal that congestion is building before it reaches a critical point, if you will. Now, in terms of queuing delay, with classic congestion control, we see this phenomenon known as buffer bloat. And this is where, as I touched upon earlier, packets are getting stuck in large buffers and ultimately this will slow the rate of transmission. And this is another concept that we'll explore in more detail momentarily. So with L4S, queuing delay is kept very, very low. So As we encounter congestion, we let the sender know. The sender backs off a little bit with their sending rate, and this means that queues don't build. So we don't see lots and lots of data being stored in buffers and lots of queuing traffic. The aim here is to keep the queue as low as possible. In terms of packet loss, its role in classic congestion control, as we've mentioned already, is it's used to signal congestion itself. But if we wait until packets are actually being dropped, then as I've mentioned several times, it's kind of a little bit too late at this stage to manage this efficiently. And with L4S, we actually minimize packet loss. So because we're using those frequent small indicators that congestion is building, what we do is we keep the queues low, so we prevent packets from being lost as queues build and buffers become full. And in terms of throughput, what we tend to see with classic congestion control is this very, very characteristic sawtooth pattern where the sender is transmitting data, it encounters packet loss, and it will cut its congestion window or its sending rate by 50%, and it will then rebuild slowly. So we have quite a dramatic drop in the sending rate, and the sender will then gradually ramp up its sending rate because we've detected there's congestion, so it doesn't make sense to be transmitting at the full rate. We need to back off a little bit, or in some cases to quite a large extent, to allow the congestion to be reduced. Now, within L4S, as we will see, this is a much more scalable, much more consistent approach. So we don't see these dramatic decreases because we're not waiting for packet loss to occur. We're taking a much more gradual, steady, measured approach. So we're constantly adjusting the sending rate by giving feedback to the sender as to what the current conditions in the network are. And we're managing congestion to an extent, but we're not waiting for it to become serious enough that we need to back off by 50%. Now, to illustrate this further, we can take a look at the characteristic sawtooth pattern that you see with traditional or classic TCP congestion control mechanisms. So if we take this example, we've got the blue line that represents the buffer capacity, so how many packets or bytes of data can be stored and queued in a buffer. Now, what we can see here is when the sender initially starts transmitting data, this is a nice, slow, gradual increase, so a slow start. And as you can see here, when we hit the capacity of the buffer, packets will start to be dropped. And this is where packet loss will be signaled to the sender. Now, what we see now is the sender sees this packet loss and says, okay, I'd better start lowering my sending rate. And what it does is it decreases its sending rate or its congestion window by 50%. So this is where we see that sharp drop. What the sender will then do is it will gradually start to increase the transmission rate. We don't want to just go at the same rate as before because obviously we know that the buffers are full and that we'll just see lots more packet loss. So we take this steady and gradual increase, and this is how we get this characteristic sawtooth. So we increase until we see packet loss again, we back off by 50%, we slowly increase. Now, one of the key drawbacks of this way of doing things is that gradual increase means that potentially we're not actually utilising the full capacity of the network link. So we're actually wasting bandwidth. So the problem that we solve here with L4S is that instead of taking these really significant drops, we signal congestion much earlier and we take a more gradual approach to reducing the sending rate. So as we've mentioned, this is a much more proactive approach, whereas this would be very reactive. So this gradual climb and then this very, very quick and sharp drop is what we call additive increase, multiplicative decrease. So the idea here is that we steadily increase the data rate just to make sure that we're not further adding to congestion. However, when we hit the limit of a buffer and we see packet loss, we then see that very, very significant 50% drop to the sending rate and that gradual increase again. Now, I've mentioned the concept of buffer bloat already. And to define it further, it's a term that we use to describe a degradation in network performance that is caused when buffer sizes at network gateways are too large. And what we see is large amounts of queuing traffic in these buffers. And because the buffers themselves are quite large, we don't see packet loss until the buffers themselves are completely full. And we can use this analogy of pouring water into a container. Now, in this example, we can see that there is already data being held in this buffer. So there is water in the container. And we can see the pipe that's coming in is the kind of perceived capacity of the link from the sender. So the sender thinks, hey, I've got all of this transmission capability. I'm going to pile as many packets as I can on this link, or I'm going to send as much water through as I can. And the output at the end is where the data is actually flowing out of the buffer. And the problem that we have here is that if buffers are too large, it takes a while for packet loss to happen. And as I mentioned earlier, in traditional congestion control mechanisms, we need that packet loss to signal that there is congestion in the network. And if it doesn't happen, the sender thinks everything is fine and just keeps sending that data. And what we end up with is a lot of packets or bytes of data being stuck in a buffer. And what we see here from the kind of outlet pipe, if you will, is this is the actual capacity of the link, because we need to consider the traffic that is already in the queue. So if we expand this further, the data flows in, it's then stuck behind the existing queuing data in the buffer. And if we think about real-time communication or applications that are incredibly delay critical, we can't have these packets queuing. They need to be able to get ahead of this queuing traffic. And we have no mechanism of doing this in classic congestion control, unlike what we have with L4S. So with L4S, we actually combine a different approach to managing congestion with a different approach to queuing, which means that our delay critical packets don't get stuck behind other traffic. So what happens with buffer bloat is the actual link capacity is constrained, and the data flowing out of the buffer, as we see with the water droplets, is very, very slow. So the idea behind L4S is that we reduce the amount of data that is held at any given time in buffers, particularly for latency critical traffic. And we'll explore this queuing mechanism in more detail later on. So the idea here is that to reduce this, we need to reduce the amount of data being held in a buffer. And with L4S, we have a specialist buffer that we keep the queuing very, very short so that real-time packets are able to flow at a steady rate. So for certain types of traffic, if you're waiting for an email or waiting for a web page or an image to load, this isn't really a big problem. But the problem comes when we've got that real-time traffic, when we're potentially streaming video, for example, is another use case that we might see, where those incoming packets are getting stuck behind queuing packets. And it's a little bit like being in a supermarket. You've gone in, you need some urgent medication, let's say, and you're stuck in the queue behind lots of people who are just doing their weekly shop and not in a particular rush. So with L4S, we can give priority to delay critical traffic, and we can reduce the impact of traditional congestion control, and we can mitigate and eliminate the effects of buffer bloat.